you can solve it numerically. Okay, so this is the idea for today's class. All right, so I will take a look of our notes. I hope I still have here. All right, so we take a look back the example 6.1 that I haven't saved last time. Don't do this, yeah. So next time, please save your what they call it, code. Okay. So when we want to, for example, to solve an ODE, right? So you are given some function of ODE to solve. In this case, it depends on two variables, x and y. The last time that we did for this one is actually 1 minus y, right? So this is your function, and then we are going to solve for your ODE. We have a certain loop. For example, we're going to solve for a certain number of n, right? And from there, we know that the Euler's equation is given by yi plus 1. So I just mark as yi, okay, equivalent to your y naught, the initial value, plus step size times your function. Okay, so this function, since our value is given by y naught and x naught, so eventually you have to make sure that you call your function properly. Okay, so after that, you just print your result. So we want to check at what iteration that we're going to have our solution, the value of x that change, and also your answer of your yi. All right. So in this case, that we have to declare our initial value, right? So what is our initial value in the example? The example, we are given our x naught is 0, our y naught also 0. Okay, so the range is you have to calculate from 0 until n, right? So in this case, we are going to have our step size for certain range. Okay, so now definition of our h is 1 over n, right? So now we have to declare what is our n, and is 10. Okay, so it means that you have to make sure that our x will increase by 0.1. Okay, so from there we have to make sure our x is add by one step size, so it will go to the next value. And another one is, okay, now h is being declared. So what else? Now, okay, x naught, y naught, right? So since we are going to use x naught here, so we can eventually put this one is x naught. It means that the x naught will be updated frequently, yeah? So that you have to get the new value. And after that, so since the printout is, if you want to do x like this, all right? So what happened is either you do like this, okay? But in this case, we just swapping the, what they call it, variable. And after that, we can update it, what is our x, right? Another one is we have also to update for our y naught, right? So what is our y naught, right? So the new y naught is just equivalent to yi. Okay, so you can see here, now the, what they call it, the code, the print is complaining they don't know what is x here. Although we already declare x is here, but in coding, they have to read line by line, all right? So if you have something like this, it means that you have to either to put it x not like this. Okay, so if you put like this, you can see there's no longer error. So we have to remove this. Or if you want to put it x, so it means that you haven't, no need to declare as a x naught, just as z, right? Okay, so and then you run your code. I hope you can see this. Okay, so you can see here now we iterate until 9 iteration, right? So you can see here now our x is increased by 0.1, right? So if you want to increase exactly 1, we just plus 1. And then you can see it's until 0.999. It means that it reached until 1. Okay. So how that we want to visualize this one in graph, right? So you can visualize this result in graph. So how you want to do this, right? So definitely you have to import your matplotlib if when you want to visualize your result. All right. So now we are going to print your result here, right? You want to see how does it look like. So for example, you want to see what is your y not yi look like. Okay. So then you have to npl show. All right. So if you do the coding like this, one thing that here we are not in what they call it in tuples or in a proper way to plot. If you just plot like this, what happens is when you run your code, you won't get any lines, right? So let's see. You can see here empty. Why? Because the value that produced here does not transform into what we call numpy of numbers, right? So that's why you cannot see anything. So if you have it like this, don't panic. What you should do, we just put some what they call it, marker. Okay, so you can put marker something like this, right? So this is marker so that they will, all the number here will produce as a X here, right? So you can see they produce like that. If you, this Y is in rainbow because they just according to the RGB color mode. RGB is red, green color mode. Yeah. So if you want to make it just a very similar color, K is for black. And then you can see this is how the solution of the Euler's method solve for your ODE. This is for fs y minus, 1 minus y. Okay, so from there you can see this is the result that we solve. Okay, so for this one, you can see that here, if you want to see the axis correctly, you see that you can see that here each point is being have the h 0.1. You can see it start from 0 until 1. So it will solve until it converge or it solve until around 0.6861. The solution is around here. It's approximate solution, right? So if you want to see what is the line, the real value, what you can do is you have to declare another x value. Okay, so this is for the, what do you call it, the exact value. So you just declare numpy a range, for example 0 until 10 accordingly. This is for the another, what they call it, line. So then I plot for the real function. Now this is your x, and now you have f x y. Okay. Oh, they want some, you have to import numpy. Okay, you can see here again, they don't understand what is the value of y. So in this case, you can put this one as a y naught, for example. Okay, so and then because what is, if you just put y, the code don't know where to find y. So here our y is 0, it start as 0, okay? So when you run this thing, okay, it will complain. Why? Because of the shape is not the same. Why is the shape is not the same? I think because of the range of your fx and y naught. Yeah? So in this case, how to solve this? All right. So when you have this kind of a problem, you can see here when you put your y here. All right. So what happened? So definitely it's just 1 minus 0, and then it doesn't iterate. So how that we going to make sure your real value got answer? Can anyone think how to solve it? I can hear someone is trying to talk. All right. So how that we want to put our proper x? Okay. So now this what they call it function is not being solved. Yeah. So when you have this kind of things, you have to see that how that we're going to solve this problem. And from there, we are going to see that either the value is correct or not, right? So hold on. Who's is having some rainy days outside? All right, so why you cannot solve it? So what happened is this is unsolved function, all right? So when you want to solve for your real value, what you have to do, you have to evaluate your ODE first, right? So you evaluate your ODE. So what happened is you need to find what is your y prime, right? So when you have to evaluate your y prime, sorry, my cat is sneezing now. So what you should do is you have to find what is the real solution for your Euler method. Hold on, there is someone coming here. Is there anyone else still online? Okay.
Yeah. Still trying to figure out.
Okay, so how that we going to put it the value inside this what do you call it, function, right? So what you should do is you have to evaluate by hand first the function, because why? When you put your what you call y here, right? So y here, the initial value of y, what happened is when you put y here, it's just written to one value, right? So when it's written only to one value, it means that this plot won't produce lines. Okay, so when it doesn't produce line, it cannot plot. That's why you have this error. They say x and y is same dimension. It means that the value that we calculated, they only give you one value or one pair. So it cannot plot because it does not reflect to this thing. Okay, so when you want to solve this, hold on here, I'm going to see the code that I've done before in different machine. Excuse me. It seems that my cat is in front of the computer now. Okay, so remember that we are going, so now instead of, we have this function. So this is our, what they call it, ODE. Okay, so then we have to find the analytical value. So what are the value that can be changed. The only value that changed here is your x, all right? So remember that last time I just give you how to solve it analytically for this one. So I just now, okay, I have to produce another function. This is the analytical value. Why I put p? Because I don't want to what they call it, make it the same as f. It is f, but I just want to make different names so that it won't be conflicted when we calculate. All right, so the analytical value when we evaluate this function is given by return 1 minus mp exponential x. Okay, this is the one that we discussed in the class last Wednesday. Okay. This is we have to solve the integral, the dy dx, right? So now we should able to get some nice function here. Let's see either it can be plotted. Okay, so this is your real function. Oops, sorry, not 10, 1. Okay, so now this is the what they call analytical value that you evaluate from this one. If you still remember that we have to evaluate the exact solution, or this is what we call as a exact solution. And this is our analytical value that we calculate from Euler method. Hold on, someone is coming in. All right. So you can see here there is some difference, yeah, in this value. So this is where the error come from. Okay. So it does not really solve or it doesn't really cross all the points, but they have some divergence. Okay, so this is accumulated by the error of the Euler method. So that's why it's just an approximation, right? So when it's approximate the value, it means that now what happened is they have some certain value which is you can see the difference, right? So when you have like something like this, you can calculate the error between these two, right? So you just get your, what is your yi, you minus with your px, and you can see how much the error is. So we can see how much the error that we produce, right? So for example, error, we want to see, which is now should be your yi minus your px. Okay, this is also will come from because of the numpy range that we calculated. Okay. Now will be x naught, yeah? Because x will change. So we print again the error. Okay, you can see here we have some error here. Okay, so this error is defined by the difference between these two plot, right? So you can see it getting smaller and smaller when you try to solve it, because this one we can't really see it. It's getting smaller because of maybe the scale of this thing. So when you calculate this, you can see that how much the value will change. Okay, so when you plot like this and you find that it doesn't go to 0, it doesn't go to 1, you just increase the range. Okay, so for example, you increase 1.5. This is 1.4, maybe not much, maybe 1.2. Okay, so just to see that how much it will goes to 1, right? So here we get the Euler solution for your both analytical value and also your numerical. Numerical is given by this x here, and this is for your exact value. Okay, the shape or the pattern should be the same, although it might not be exactly close enough, but this is due to the some numerical propagation. This is what we call as the error propagation. Okay, so this is for Euler's method. Right. So next, we are going to see how about Rajputa. Okay. We have another one more method, which is midpoint. You can do the same for the midpoint, right? But the midpoint is usually not that being used a lot in ODE. So I put some now RK2. Okay, just to give you some very general information. When you install something, for example, so some code, whatever, you can see here we have this kind of comment here. What does this comment mean? This comment means that your Python being installed at this particular path. This is what we call as path. It means that your Python 3 is installed as in USR bin environment. Okay, it depends on your computer system. You have this kind of thing. So if you are later on, maybe you have become expert in everything. You don't want to use this kind of auditor. If you still remember, I use a lot of terminal, right? So when you use terminal, so you have to install everything manually, and then you have to make sure that your code or your software should go to the proper path. This is some just general info that, for example, maybe one day you choose to work at the IT company or something like that, or you have to set up your own supercomputer. So this is some idea how you can install where is your software is. Okay, but if you use Windows, you just click and run everything. It will do it for you. So if you use different system, you have to do it manually. Okay, so enough of the what do you call it? The the IT stuff. Okay, so we move on to the Rajputa method. Okay, so Rajputa method, we see that how we're going to solve by using the same example, but now we are going to write the code for RK. So when you see RK, so this is for Rajputa method. Rajputa method, sometimes it can be tricky. For example, if you see that there is, we have a lot of variable involved. Okay, before I write the proper code, we just identify how does it look like. So RK, they should have K1, right? K1 is given by your function, fx. They should have K2. Okay. So K2 is given by, so your function x plus h, comma, y I plus h times with your f x y, right? This is before I do anything else, just to see that how does it will eventually come in our coding later on. Okay, so everything is defined by, this is, if you see in the notes, is x, y, y, I, right? This is how it look like, right? So in this is in our notes, right? So then what does the formulation will give you? So your yi plus 1, okay? So now, for example, so your I plus 1, okay? So it's actually your summation of your yi plus your h over 2 times with your k1, k2. Okay, so maybe sometimes you might be confused when I write a code. Sometimes I use bracket, this square bracket, and sometimes I use just normal bracket. It depends on your usage, because I'm so used to use the normal bracket. The square bracket is something that unique for Python actually, right? So if you used to write a code in a different language, square bracket is not something popular. Hold on, I'm going to remove my cat temporarily. Just stay tuned. Okay, I'm back. Sorry for the interruption. Okay, so now we have this formulation. Again, we have to iterate for a certain value, right? So when you have this, right, so all this value, then we have to identify again what is our function. Just like just now that we did. So when you do coding, I want you to practice that. Always put everything in some floating number, because why? This one will cater that your result will. This is will avoid to have some what they call it, rounding error or truncation error. Because why? For example, rounding error. If you sometimes you put one, they will see as an integer, and when you divide with something certain value, it round the value. Okay, so we want to avoid that. So if you put like 1.0 or something, it will always see as a real number. Okay. So now again, we going to use the same example. Our x naught is a 0. Then our y naught is also 0. Okay. So now we also have our h. H is 1 over n. Okay. And n is, for example, your 10. So then, again, we are going to write in range, okay, of 0 until n, for example. We're going to test it first. And obviously, everything should go here. Okay, it's still complaining because we have xi and yi, right? So if you want to retain like this, another trick is you can do is just you put xi equivalent to x naught. Okay, y naught. Okay, now it's complaining now y is not defined. Okay, so y is not defined. When we put anything in a square bracket, now it becomes some normal y, not just yi plus 1. Okay, so either you do like this. You don't do like this. Eh? If you do like this, it means that your yi is plus with exactly 1. It's not that I plus 1. Okay, so when you do like this, so your yi is now changed. So does it will give you some a problem? Yes, because now it will confuse with this yi. Okay, so either you do like this. I think your yi plus, I think. Let me see. I have to remember back the Python coding. is plus 1, right? This one is something like this. Okay. Let's see. If it's not working, then we are going to use the normal one that I always do, like in the Euler's method. It's just that we define different variable. Okay. So you just print the result. Okay, another one is you have to iterate for your x. Eh? So your x will be your, now will be your xi. Okay, so your xi is equivalent to xi plus h. Okay, we'll see that how does it give. All right, so it gives some, can you see the value here? I think the result is incorrect in somehow. You can see here, this is from Euler's method, and this is coming from the RK. You can see how much the difference? A lot, right? So you can see that first is okay, but until what do you call it? 10, you can see here by using Euler method, your result at n is 9, it should be around 0.65. But using RK, using this kind of trick, what happened is now you become 65. Okay, so this is not a good thing. It means that it will calculate twice. So what happened is, what I'm going to do is, I'm going to put like this, right? Just use the traditional way that I'm used to it. Okay, so it's up to you to modify according to your needs, but this is the simplest way to do it. So now yx is actually yi plus 1. And now you can see the result using the Euler's method here. And using the RK should be approximate the same, in the same order of magnitude. Okay, so now it's like this. Although the value is not exactly the same, like just now I put y plus, okay? So you can see it's 65. 65 means the order magnitude is totally different. It is a one order magnitude higher. Okay, it should be written around 0 point something, right? So from here you can see that the result is a bit, although it has certain error, but the result is in the same order of magnitude, right? So you can do the same, just like I did for Euler's method, to see that how does it look like. Okay, I just plot for, you can add for your exact value later on. Okay, so we plot here. Okay, so there's no marker. We provide some marker for the Python. Okay, you can see here the plot. Either you use Euler or you use RK. The plot should look the same. Okay, so this is the Range-Kutta order 2. Okay. Of course, obviously the result won't be exactly the same decimal places. This is due to the, in the Range-Kutta order Range-Kutta method, what happened is the expansion of your function for K1 and K2 will provide for the higher accuracy of your calculation. So that's why you can see that when you put all your value, you can see that here your function K1, K2, and then when you calculate for the RK, it will improve the solution of the ODE, right? So this is for the RK2, okay? So how about for RK4? So for RK4, the difference is you're going to expand your K, right? So I just save as I save a copy. RK4. Okay, so now we do for the RK4. So this is how you do the coding. You just save as and then you can just modify to whatever that you have. Right, so RK4, how does it look like? So RK4, we have another K3 and also K4, right? So again, we take a look at how this K1, is it the same? So K1 is Fx Iyy, K2 is Si plus H over 2. You can do like this, over 5. Okay, so this is why I remove this. Yi times 0.5 times K1 equals 8. And what is K3? K3 is also the same. So this is K2. And K4 is, I take this one. And this is X plus H. Then Y plus H times K3. Okay, so the function now is a bit different. Now this is over 6. K1 times 2K2. To K3 and then plus K4. Okay, so now this is for the RK4. Let us run and see how does it look like. Okay, you can see here for RK2 and RK4, okay, the result become, they also have certain different in decimal places, right? So this is RK2 0.664, and then this is RK4 around 6.67. It become closer and closer. Obviously, the plot is just the same because I don't change anything. Okay, all right. So either, so you can see YX, just the same, either Y X or Y should be give you the same plot because we just swap the value. Okay. Oh, forgot to add. If you use a different editor, always put show. Nanti dia it won't save if you don't put show ni. Okay. So right. So this is the 3 method that we learned for Euler's method, RK2 and RK4. Any questions so far? I hope all of you can follow.
No questions.
No question. How about others?
No doubt, sir.
Okay. It seems that you can do it. Okay, now this is a very simplistic problem where we use what they call it, function kan? Function that you know what is the function and then you transform it. Okay, back to our discussion in last Wednesday. We discussed that how we're going to transform the example in chapter 1, if you still remember that we did for the buggy jump, into all this form. Okay, so now, right, so I open back again that slide. Okay, I want you to tell me how to transform in this equation that we just did just now, starting from the Euler's method, right? So hold on, let me open the file first. And I want you to do it here. I'm going to share another file. All right. So these are the chapter 1 that we have discussed earlier in the semester. Okay, so if you can see that this is solved by using Euler's method. Why it doesn't go to the next page? All right, so this is the problem that we are going to solve. Okay, so you are given all this value. All right, so they say design a suitable algorithm for this problem and develop a Python program based in algorithm. So actually in this example, it was solved by using Euler's method that we just learned just now, right? So from here, okay, so how we want to transform this into some ODE equation, and you can solve by using Euler's method. Okay, the approach is given, all right? So approach, this is mathematical approach, and this is you are given some analytical solution. So analytical solution, you can change with respect of t. G, M, and C is a constant. Okay, and then you calculate in terms of time, and also you iterate. You can see now our initial guess or our starting point, our initial boundary problem is given by V naught 0. Okay, so we're going to calculate until what time that we want to iterate. And the numerical solution, finite difference is technically the Euler's method. Yeah? So we solve this formulation. So it's rate of change of velocity with time is given by this formulation. Okay, so the gravitational minus C is a constant, some I think drag constant, and mass. This is mass, and this is where the velocity depends on t. All right. So when you solve all those things by rewriting all this formulation, what happened now? This is the form of Euler's method. This is your y, yi plus 1. This is your yi plus this is the this is for x actually. Sorry, this t is your x, and then you can solve this thing. So my question to you now, all right? So we have a look at our equation, our Euler's equation or formulation. All right. Now, how we want to transform this into Python code? Okay, so first of all, you already have all these things. Okay, so how to start this calculation? So before you do anything, what you should do is you create an algorithm to solve this. Wait, why is my iPad not moving? Okay, so I want, we'll see back our code just now. Let me share everything. Stop sharing. I'm going to share my entire screen. Okay. All right, so we move back to our Euler's method here. Okay, and also we have our formulation here. I hope you can see both of this, right? So here, what is our defined fx here? Anyone?
That would be V.
V?
It will be VT, right? Because later we will iterate VTI plus 1.
Anyone else? So the function, all right? So you see now what is our function now? So our function will become, what is our x now?
Oh, so fx plus y will be written y plus dv dt. dy over dx,
dy over
which
dx.
is and multiply by delta x.
Okay, so now, right, so our function now is actually, our x is t, okay, so our y is v. That is our first function, okay. So instead of fxy, so it's become f tv, all right. So that is our what they call it, function. And what is our the equation is actually our yang itulah our slope of our gradient tu, okay. So that is the what you should put in the return, right? And after that, what is your x naught, right? So x naught is okay. So x naught is actually your t. So now t is 0, and y naught is your v. V is 0, and then you have to declare also everything else, your m, c, and so on. All right. So and also you have to declare your g. Yes. Anyone want to say something? Okay. So from there you can start calculate what is the Euler's method. Okay, and then you should get some solution. Okay, so your now instead of y is actually your v, right? Okay, now so your solution, your yi here is actually your vi, and then y naught is your v at t0. Okay, so it means that yi is where the velocity at the time increasing. Okay, and this is where your initial velocity. All right, and then this is the function of the calculation. Right, so coming here, and after that you can calculate until what time. Okay, so the question here, it doesn't say that until what time is going to fall. So what happen is we can estimate. You can vary your h, right, until at what time it will hit the ground actually. Okay, so from there you can see that when the solution is become converged, it does change. So you can estimate what is your solution. So h here you can change by your own. You can set until 1 second. So this is in second. So if you want to set until for 30 seconds or 1 minute or how many hours, okay, you have to carefully calculate your n, because n here will assume how many duration of your time, and then you have to calculate. So then your analytical value is already given here. This analytical solution. Okay, so you replace your p with your vt, and then put everything and you iterate in terms of your t, right? And from there you can see the solution of either your Euler's method will solve your solution. Okay, so this is one approach of how we apply a physics problem inside the Euler's method. So you can also redo everything back again using RK2 and RK4, and then you can compare your answer. Okay, so that is one thing I want you to do. All right, so please show me your result by next Monday. Okay, so another thing is I already prepared some tutorial for you. I guess I open it here. Please open your spectrum. I think my computer is hanging because I opened a lot of things here. Let me stop sharing first, so it will appear accordingly. So I already provide you tutorial 6 and 7. So first we have a look for tutorial 6 first. Okay. So not many questions, but please do it. Okay, so for tutorial 6, right? So it's you have to approximate what is the Euler's method. Instead of y x naught, we just do for our exercise just now. Now your y is x is 1, right? So and then you solve the following problem, okay? And see that either you get at y x equivalent to 1. It means that your x is start from 0 until 1, okay? So you solve all those things and then you repeat by using, sorry, this is RK order 4, not order 2. I'm going to update later on. Okay, so after that, okay, one thing that I haven't discussed doing coding is another one is using the Adam-Bashford. This one I'm going to discuss next Monday. All right, so how to solve this, right? So first you are going to use Adam-Bashford method with a given h, right? So you solve, in order for you, before you can use this, we are going to use Euler's method to generate the starting value, which is yi plus 1. Okay, so have a look how this Adam-Bashford equation look like, and then we are going to generate Euler's method first before we insert into this prediction character method. Okay, so that is the fourth one. And then number 5 is by using equation what you call coding that I just show you just now. All right, you're going to solve for 1b because we have both x and y, right? And then we solve it by using h, a very small h, which is 1/16. Okay, you solve it and then you try to get your answer. Although it is different in terms of decimal places, it should get, this one should get you the greater accuracy. Okay, so that's all for today. I think I'm glad that I'm able to finish for RK and also all those ODE. Okay, so next Monday we are going to discuss about this tutorial and also the numerical integration. Numerical integration, okay, so you are going to learn to do 2 types of coding. One is for the basic integration rules, which is basic, midpoint, trapezoid, and also Simpson. That is very simple. Another one, the tricky one, is the composite. The composite one is a bit tricky, but you have to learn how to code and also to solve it using the tutorial 7 later on, right? So tutorial 7 is also already uploaded in Spectrum. Have a look, right? So this is how does tutorial 7 look like. Let me stop sharing. I share back again tutorial 7. Okay, this is tutorial 7 also in your Spectrum, right? So this is first you learn how to solve using a basic numerical integration. And the second part is you are going to use a composite modified method where we are going to deal with the step size. Okay, and from there you are going to observe how the error propagate when you have different h. Propagates means that how much the error increase or decrease when you have a certain different h value, right? And after that we're going to write a code for all these 6 methods, and then we're going to solve it. Okay, so this one we shall discuss on next Monday, half an hour. So I think that's all for me today. Any questions so far? I think at least 25 of you should be able to get the idea how to do this, right? So the things that I just show you just now, Euler's method for chapter 1, you know it